6 is here, and we have 50 minutes standing between you and spring break euphoria, I believe. So let's see if we can get through a little bit on mechanical properties, and then you can head off onto the break. What we want to do is we're going to pick up where we left off last class, talking about the difference in stress-strain behavior for specimen length. So as we go to our slide here, we can see that we left off on this slide that I think was at least shocking to some people to learn that the stress-strain response of concrete was not a material property and depends actually on the length of the concrete specimen that's being tested. The longer specimen tends to behave in a much more brittle fashion than a shorter specimen, and this has really to do with localization. We're actually going to go through the reasons for this as we go through today's lecture. The basic idea here is that in the pre-peak region, especially up to about 40 or 50% of the peak load, really what you've got is distributed microcracking. And I've drawn that here with using the Microsoft PowerPoint little stars. But the basic idea here is you're going to have relatively distributed cracking occurring throughout the entire sample. As you start to get above about 50%, 70%, you're going to start to see these cracks coalescing into certain regions where some of this microcracking is going to be connecting. You're going to have a couple different interfacial transition zones connecting. The noises will actually get a little bit higher in amplitude. There'll be a little bit more energy consumed. Once you get to the peak, what's going to happen is the specimen is going to break up into two distinct regions. So I've drawn on our right-hand side something that looks very clear. It's not like the specimen changes color or lets you know where the two distinct regions are, but you basically have a region that we're going to refer to as the bulk region, and then you've got a region that is the localized or the failure region. So on the edges of this particular sample, here and here, we have the bulk behavior of the specimen. In this center region, which is shown here in black, we have sort of the localized region. And what's happening here, I've drawn a stress-strain diagram in each one of these regions to show you the difference in material behavior. Again, up to peak, you're going to see that this is going to load right along this green line here. It's going to load up to the peak value. You would get exactly the same behavior going on inside of the failure region. Where you get a big distinction, where there's a big difference in the way these materials respond, is once you hit that peak load, once the system begins to localize. What happens in the bulk region is the specimen is actually going to start to unload, and we'll explain why in a couple of seconds. But inside of the cracked region, that crack is going to start opening up, and that crack is going to open up and it's going to be able to transfer less and less stress. So what's happening is the amount of stress that it can transfer is decreasing as you open that crack further and further. And this kind of makes sense. Imagine if you had Velcro and you start to separate that Velcro a little bit apart. That Velcro is not as tightly bound as if you really get it in there and mush it tightly together. So as the cracks begin to open up, they can transfer less stress across the cracks. So as the strain is increasing, as the crack is opening up, the amount of stress that it can transfer starts to drop off. As the stress starts to drop off in the cracked region, what happens is the other portions of the sample begin to unload. They're not necessarily going to keep increasing their length. The stress is going down, and since the stress in the bulk region has to be equal to the stress in the local region, or the damaged region, or in the crack region, this is simply going to unload elastically and go back to some value. It may be 0 or a number very close to 0. But the basic idea now is you've set up a system where you've got the ends of the specimen that are behaving elastically, and you've got a localized damage region where all the damage is occurring. All of the energy is being consumed in this particular case. So all of the energy is being consumed in this black region. What's interesting about this is, irrespective of the length of the specimen that's being tested, the same amount of energy is consumed to fail that specimen. Right? So the amount of energy that goes into the failing of the specimen is really dictated by the volume of this localized region rather than the volume of the overall specimen. So what you can start to see now is now this is starting to make sense. What we've got is we've got this localized region that's going to be a fixed length. All right, from a lot of the work that's done here, we show that it's about the size of the diameter. Maybe it starts out the size of the diameter, goes up to about 1.5 times the diameter. The damaged region is fixed in length. So as you make a specimen longer and longer, what you're increasing is the portion of the specimen that's going to behave elastically. It's going to unload. once you get past the peak load. This is why you're going to see this having a much more brittle response. More of the specimen is simply unloading. Less of the specimen is undergoing this localized damage development. So you're going to see a much more brittle overall response. Now the question is, why do we even care about post-peak? Does anybody care about post-peak? Anybody who's not headed to spring break care about post-peak? Mike, you care? Oh, okay, you got an answer.
Wouldn't that dictate how it fails, how fastly it fails?
It's going to dictate a little bit about failure, but we actually inherently, we assume the post-peak response almost every single day in reinforced concrete design, but never actually stop and think about it. If you'll remember, it's probably the second day of reinforced concrete design, maybe the third day, depending upon how an extensive job they did introducing the syllabus and showing you the first 2 or 3 flyover chapters about the fact that concrete was a material, and then we jumped by that pretty quickly. They did an example that looked something like what we see up here at the top. They took a piece of concrete with some red reinforcing steel in it. They put it into flexure. They drew a strain section, right? They said, what happens if we start to put this into flexure? It's going to be in tension at the bottom. It's going to be in compression at the top. We assume the concrete doesn't do anything at the bottom. We assume all the compression is coming from the top. The bottom, we've got all of our tension coming from our reinforcing steel. All of the compression is coming from the concrete. We can draw a stress-strain response that looks like this. And it's way too hard to do that. So in 1902, Whitney developed a stress block. We are going to approximate the actual stress-strain behavior as a rectangle. And the entire post-peak response of concrete was lost forevermore. All right? But it's actually kind of important, because here you can see this is the peak stress. This is the strain that's 0.002 or 0.003. When you're designing for a 0.003 or 0.004 type of behavior, there's a good bit of post-peak response that's considered in your stress strain portion of the diagram that you're approximating. All right, other types of responses where you might be using this. Pulling concrete in pure tension. There is a component of post-peak response of the concrete that is actually going to come in and dictate the overall response of the composite. Moment redistribution. A lot of times you get the advantage of being able to redistribute moments based on a whole bunch of factors. All of a sudden you can just start shifting moments around in reinforced concrete design. Basic idea here is there's creep, there's microcracking, there's some additional relaxation that's taking place. So a lot of times post-peak is kind of an important thing, but it's sort of an abstract concept, because most of the time when you take a cylinder, you jam it into a machine, you don't see that post-peak behavior. You see a nice stress-strain diagram up to peak, and then kablooey, exactly, it explodes. And you say, well, how do we get this actual material response? Well, there are a couple ways that you could do this. The way that we would sort of go here, and as I learned last night at the dating auction, there's been no new music created since I graduated, so I actually feel much younger now. I don't think there's anything, I think the newest thing that was played was about 84, 85. But if we wanted to go real old school, we could take and we could do a post-peak test that looks like this one that we see here. And this is the way this testing was done. I'm going to say 50s, 60s, 70s. This would be the way that you would have gotten the post-peak response of your concrete. You would put this into a testing machine, and I showed the testing machine being horizontal. It would work just the same if the testing machine was vertical. You were going to push on a steel platen, another steel platen. You were going to push these together. You would put your concrete in parallel with steel. So you would either put 2 steel bars, or more frequently you would put a steel cylinder in the system, and it would be in parallel with the concrete. So the basic idea is that you would get a composite response of the stress versus deflection. You know the impact of this steel. You know the stress deflection behavior of the steel. And the difference between those two, the composite response minus the steel, should give you the overall response of the concrete. This gives you a way to control the deformation of the concrete so that you can start to capture some of this behavior after the peak region. Now, one of the big problems with this, can anybody guess what one of the problems with using this type of an approach is? Oh, it's a very, very sad Friday afternoon.
Spalling?
All right, spalling may be a problem. All right, there's a little bit more fundamental issue. Making sure they're both the same length is not trivial in this particular case. The other big issue here is when you get up into this region, you're trying to measure these real small stress values inside of the concrete, and you're taking a huge stress out of the steel, subtracting that out of a huge stress for the overall composite material, and you start to lose resolution when you get out into this part of the stress strain diagram. So what people really tried to do is they said, are there ways that we can capture the behavior a little bit better? So what is...
If you have to go through all of this to determine what it does, and yet if you just test it, it explodes, why do you have to do all this, A? And B, when would you ever have steel in the compression zone in which the concrete and the steel would both be acting in compression?
Okay, there's two things in there. I'm going to take the second one and then come back to the first one. Where would you have the steel and the concrete in compression like we see on this diagram? This is a particular testing method to try to prevent the concrete from failing too quickly. So this is not necessarily set up to mimic a particular, you see this in a girder, you see this in... This is set up to really sort of mimic what's happening, to try to slow down the failure process so you can capture what the material is actually doing. The second thing is, where would you actually use this? I would say that you use this more than we think we would. And the main aspect of where you would be using this is when you design a concrete structure, you very infrequently design it without reinforcing steel. Right? You always have spirals in there. You always have, hoop reinforcement. You've always got your steel reinforcement. And one of the things that you're actually counting on is you're counting on the ability of that concrete, even after the maximum stress has been exceeded, for that concrete to still have some resistance. So in an earthquake, for example, the entire building doesn't collapse just when one part of the concrete structure hits the compressive strength. All right, so once those cracks start to open up, once you start to get into this portion of the behavior, you need to know some of the more intricate response. Now the question is, do you need this on an everyday basis? No, you could design your reinforced concrete structure never getting past 30 to 40% of the stress. And in fact, that's what a lot of engineers do on a daily basis. Right? With your design codes, you stay below that level because you don't want to deal with creep. You don't want to deal with anything that's not elastic. You don't want to deal with this softening behavior. So you try to keep the loads down as low as possible. But you can see here, this picture of designing a beam and flexure isn't that far off from what you saw the first day you took 473 or the equivalent reinforced concrete design. And you made an assumption about this behavior and went on. Now, I mentioned last class sort of in a casual way, in the early 80s, all of these design equations changed. All right? All of those equations came in where they started to say, well, what happens if you get the higher strength concrete? Because the field went from 3,000 psi concrete to 8,000, 9,000 psi concrete. High strength concrete is born. The equations aren't predicting what we should be getting anymore. So they went in and they altered some of those factors that take you from a stress strain response to the rectangle, Whitney stress block type response. The alpha and the beta factor, those scaling factors come in there. Okay? I would dare say that while it was incredibly important for Whitney to do that in 1902, many of us have things sitting on our desk right now that would enable us to use this entire stress strain response to design a beam. All right? Because we could actually input an entire stress strain response and actually use that directly without Whitney stress block right now. It's just, is it worth the time and effort to do that? And that's a question that people have to decide and have to answer. One of the places where I will say that the lack of understanding this comes in is in fiber reinforced concrete. If you look at one of the big, there are a couple things that have really kept fiber reinforced concrete from jumping into a lot of the structural codes, in my opinion. Okay, so you're not going to see this published in your textbook. But there are two things that keep fiber reinforced concrete from really jumping into widespread structural use for replacing temperature steel and things like that. One is to ensure that there's a certain amount of fibers inside of the system. The volume fraction of the fibers, making sure that the fibers were actually put in. That's something that people worry about. And the second thing is everybody tests a cylinder and they say, well, the strength is the same, so what are the fibers doing? Well, what the fibers are doing is they're altering this post-peak behavior. But right now there's no way to account for that in the design equations. There's no way to take advantage of that.
Leads to brittle failure, doesn't it? Most of the time the fiber reinforced leads to a brittle failure instead of ductile.
No, fibers actually take it the other way. They usually go toward ductile. Okay, and we'll actually spend a lot more time talking about fibers at the end and actually start we'll actually start to go through some calcs where you can actually bring some of this into your design. But there's a lot of work in Europe right now where they're actually getting rid of steel in a lot of their slabs for, let's say, I'll say light commercial residential types of apartment buildings, and they're designing them with just steel fiber reinforcement in them. So there's some benefits in those directions. Comments on where we've gone over the last, I would say, 20 to 30 years. Test and control is a huge direction where this has really changed. So as I mentioned, 50s, 60s, 70s, you would see people doing this test with the cylinder. Now you see people using different types of test and control. I'm going to point out 2 or 3 types of test and control here. The first one I'm going to talk about is load control. And load control is the type of test that sort of all of us imagine our mechanical testing machine is doing. If I asked each of you to test the material in the lab and I gave you, you can go to Menards and buy anything you would want. If I asked you to test the material, what would you do? Well, you would start off with your material, you would put it on a nice firm surface, and then you would start stacking weights on top of it. And if you put weight 1 on top of it and it didn't break, the obvious thing to do next would be to stand on it, put another weight on top of it, all right, and keep increasing the weight. This is a load control test. What you are doing is you are applying the load in an increasing fashion. You're saying, I'm going to increase the load that's on the specimen in a controlled fashion, and if you were to put on 10 pounds every minute, it would be exactly the same thing what we tell most of our new servo-hydraulic mechanical testing machines to do. Let's increase the load, and then we measure the displacement. Let's increase the load and measure the displacement. Increase the load, measure the displacement, increase the load, measure the displacement, increase the load. The material can't handle that increased load anymore, and we are at the condition Mohammed so eloquently described as kablooey. All right, the material fails. It explodes. All right, we have a problem. All right, failure stops right here. And this is a load control test. This is the way that most of us have seen these cylinders actually tested. Now, I would say there is an alternative. And there is a different way that you could actually test the cylinder. And instead of doing the test like we talked about before, where you're simply just applying a weight to the top of the sample, what you could actually do is you could say, I'm going to go a little bit differently, and I'm going to apply a 1/4 inch displacement to the sample. And I'm going to measure the force that it took to do that. Apply another displacement. Measure the force. Apply another displacement. Measure the force. Apply another displacement. Now all of a sudden what you see is we've gotten rid of the instability that occurs around the peak. The specimen would, in theory, no longer explode. You could now increase the displacement, measure the load, increase the displacement, measure the load, go the whole direction out, and trace out the entire stress-strain behavior. All right, so what's an example of how you do this? Everybody, I think, has had some familiarity with the surveying class where you had to go old school in case we ever break out the old 100-foot steel measuring tapes. Anybody else have that experience, or am I the only one who went to college in that era? All right, and to make sure that a 100-foot tape was exactly 100 foot long, you had to pull on it with a fish scale. right? Everyone remember you had the little thing with the hook and you pulled on the specimen until it registered a certain amount of force, and then you said we have exactly the right amount of force? Here you're talking about doing the exact same thing. Let's move the displacement, measure the force that it took us to get there. Displacement, measure the force. This can be done in a mechanical testing machine fairly easily. In fact, we can, if we go over to the lab, there are several machines that are set up to do this, where essentially they are measuring the displacement and using that to control the overall machine. Right? This is newer type of testing equipment that is out there. When I say newer, circa 1950, 60, 70. So some of you who have had the opportunity to go through the 231 or 331 lab with the equipment that's sister equipment is in the Smithsonian. And I am not lying about that. Purdue has testing equipment in the Smithsonian. It's not that type of equipment, but it's a little bit different. Basic idea here, this is a testing technique called closed loop testing. So the basic idea here is that there are a few things that are inside of the machine that you should be aware of. There's the hydraulic power unit. This is essentially what's pushing the oil typically back and forth. There's a servo valve. This is essentially a little valve that's opening and closing thousands and tens of thousands, hundreds of thousands of times a second to allow oil in and out of the system, to allow the system to actually move. The actuator is what's actually pushing or pulling on your system. Load cell is what's measuring the overall system. But the big thing that we're really interested in here, all right, we're really interested in looking at some of the other components of the system. We're really interested in looking at the controller. And this is going to be an important part of the overall testing system. Data acquisition is essentially what's just recording your stresses and your strains. And then we've got a function generator. So let's spend a little bit more time to look at this. All right. One of these things that we're going to be interested in is this idea of what is the feedback. All right. So we're basically going to do something. We're going to use a function generator to tell the controller what to do. And we typically refer to this as the command signal. So we say essentially, we want you to control a particular channel. And in this particular case, that may be displacement, that may be load, that may be something else. And what we do is we program into the system, increase something at a rate of something else. Increase force at a rate of 1,000 pounds every minute. So we tell the machine, this is what we want you to do. We program it, we type it into the computer, and we say, this is what you should go ahead and do. Now, what's going to happen here is we've told it the command signal. We are going to be measuring from the sample, from the load cell in the system, what is actually happening. We are going to be measuring the feedback. And what we are actually going to do is we're going to use this error signal to control how much this servo valve opens or closes. The error signal is the feedback minus the command. So what you're trying to do is trying to minimize the difference between what you told the machine to do and what the machine is actually doing. And you're going to make this adjustment thousands of times every second. So you're going to say, I want you to apply 10,000 pounds per minute. It's going to calculate out, in order to get 1,000 pounds every minute, I need to apply, a minute has 60 seconds, 1,000 divided by 60, I need to apply this. It's going to have a command signal, and what you're going to do is you're going to measure what's coming back, and it's going to say, nope, I'm applying too much oil. Nope, I'm applying too little oil. Nope, too much oil. Nope, too little oil. And it's going to keep working to apply the right amount to the system to minimize this error signal. All right, so that's essentially the overall goal. So the feedback is measuring how X is changing. The control channel is telling us what to do, and we're getting our overall feedback signal by the servo valve opening and closing. This is moving our actuator up and down. So when you look at one of these samples being tested, you see a sample, whether it's a building out at Bowen, where they're using one of the new MTS actuators, whether it's in the lab using one of the MTS machines, what you're actually not seeing is the fact that that actuator is actually jumping up and down a little bit every single step. And it's moving back and forth, all right, very, very, very small amount, hundreds and thousands of times every second. Question?
If you apply a load and measure the strain, you get a failure that you can't measure anything else after. If you apply strain and backsolve for the force, how does it keep it from failing at the same position?
We'll go through that in a second here. And I'll give you an example that you're probably really familiar with. At least I hope everybody's familiar with. But this, if we wanted to take this into the next example, we could think about this in terms of the concept of buckling. Right? So if everybody took a ruler or some sort of a piece of balsa wood and you started to load up that ruler, and I think you all did this in mechanics and materials type of class, you keep loading the load, right? You've got a dowel rod, you stack weights on top of it, you keep loading it, and if it's in load control, as soon as you get over that critical value, you snap that piece of balsa wood. The whole thing comes down. Right? When you actually do it in displacement control, you can actually buckle the entire system in a slow, controlled fashion. All right? So what we're essentially doing, you're not changing the behavior at all. You're really changing what are the stops on the behavior. So you're basically slowing down the way the material is actually responding to a point where you can actually capture that response. Does that?
Yeah, so does the displacement change then once you start to reach the critical value? Or do you continually go at the same increment all the way through the test?
You could change it if you want. Normally is sort of an odd word. Many times people go at a constant rate just because it's easier. But for example, in some of the tests that they're doing in the lab, when they do a test like this we'll do the exact same thing but controlling crack opening. A lot of the excitement is actually controlling the crack opening. So getting to where the specimen cracks, we usually don't mind getting there in a hurry. So what you'll find out is that they'll open it up and get to the peak in like a minute. And then they'll say, well, I'm going to waste the next half hour opening the crack so I can go in a very stable fashion. And then at the end of the test, they may go very quickly again. What they're trying to do is slow it down for that particular region where they're interested. Okay, and you'll see the same thing, like if you're familiar with people who do a lot of earthquake testing, there are certain parts of the test where they already know all the behavior that's going on there, so they don't mind jumping ahead and catching the important parts. Okay. So I think the buckling example sort of helped people to put this into a tangible, all right, if it doesn't help you, go buy a few dowel rods, try it out on your own this weekend. All right, I think what you'll notice is if you just apply force, it snaps pretty quickly. If you just sort of push your hands together, you'll notice that the resistance changes a lot, and the resistance goes down once you pass a certain critical point while the system is actually buckling. There are some other ways that people have tried to control this overall system. And what I would say here is this is an area where there's still probably a lot of new directions that people can go. In the late 80s, well, I'll say early 80s, as you can see here, there's a paper from 79, going into the 80s, there was a lot of interest in this because the strength of concrete was really rapidly increasing. Just increasing in a huge fashion. And while this is not necessarily a problem, as the strength of a material goes up, the material typically becomes more brittle. And we saw this last class where we said the pre-peak response becomes more linear, the post-peak response drops off more rapidly, the material starts to become incredibly brittle. What people were trying to do is say, how do we actually capture the overall stress-strain response of these really, really brittle materials? And instead of using the old school method where they're putting concrete inside of a steel cylinder, or this case where you actually measure the length, because you can actually get into some problems just measuring the length when you get to really stiff materials, they said, are there alternatives? And one of the things that people tried to take advantage of is they said, if I look at a material, I can actually not necessarily only measure the strain in the longitudinal direction, there's going to be strains that occur in other directions. So there's a lateral strain as well. And most of the time, we know that the longitudinal strain and lateral strain are related through
Poisson's ratio.
Poisson's ratio, exactly. Now, in concrete, that wouldn't necessarily seem to be a big benefit for us, right? Because Poisson's ratio is always less than 0.5 in a continuous material. Right? One of the things that happens inside of concrete is because it starts to crack, Once it starts cracking, we don't necessarily have this same concept of Poisson's ratio, right? And Poisson's ratio is still there, but after it starts cracking, it takes on a little bit different meaning, because what you're actually going to see is the material is actually going to experience quite a bit of lateral expansion because the cracks are forming straight up and down. So one of the techniques that people tried to use was they tried to use this idea of putting a circumferential gauge around the cylinder. Can you control the rate at which the cylinder gets fatter during the test? All right. Last class we saw that the center of the cylinder will bulk up. It'll get bigger and bigger and bigger during the test. Can you control that and get better information? Here's some data that comes from that. Here you can see the stress. All right, so these are stress-strain diagrams. On our y-axis, we've got the stress for both the cylinders. On our x-axis, you've got the longitudinal strain. On the right-hand side, you've got the circumferential strain on the left-hand side of the diagram. And this is a case where what we were just exactly talking about, where you might want to jump ahead very quickly because there's not a whole lot of expansion happening in circumferential direction before you get to peak, because cracking is relatively small. But after those cracks start to open up, you could control the circumferential strain and get a stable post-peak type of response, a little bit more stable post-peak response. People have done other things. So, and wow, those are some great eyes looking at that screen. People have done some other things, so I'm not going to spend a lot of time on this, but the basic things that people have been trying to do here is they've done something where they said, we don't necessarily want to just do load. We don't necessarily want to just do displacement. What we're really after is being able to accommodate the machine changing rates as we change stiffness. So what they've actually done is a testing technique where they've actually done something where they subtract off the elastic response, and they actually come up with a signal that is more in the sort of a part of load and part of displacement controlling the overall signal. We're not going to spend a lot of time on that. It's something that I would point out can be quite useful if you get into real brittle materials testing, but we're not going to spend a lot of time talking about it. Questions or concerns before we jump ahead and talk about something other than F prime C? All right, so at this point we should have a fairly decent understanding of what the stress-strain diagram is, a fairly decent understanding of why some parts are linear, some parts are nonlinear, what's the driving force for the softening response, and then the fact that we can sort of model this as a bulk behavior and as a damaged zone. So we need to bring those two things in. What we want to talk a little bit now is about other properties. We could change the direction of loading, and instead of squishing it, we could start to pull on the material, put it in tension, and we know that it is going to be much weaker in tension. A simple rule of thumb is about 1/10 of the strength in the compressor strength. About 1/10 of it is what you're going to get if you test it in tension. Very, very rough rule of thumb. We'll give you some better rules in a couple seconds. And you may say, well, the simple way to get the tensile strength would be to take a chunk of our concrete, to yank on it in tension. The stress would be equal to force divided by area, and we should be all set. There must be an ASTM test method for that. And I will tell you there is no ASTM test method to yank on concrete in tension. There are probably two reasons for this. One is it is a very tricky test to do because making sure that you don't have any misalignment in the system is very, very difficult. The other thing is it is a very time-consuming test. When we do direct tension tests in the lab here, they take about 3 days. They take us a day to glue the specimen into the grips, a day to go about testing that and aligning it, and a day to sort of break the whole system down and get ready for the next sample. And for those of you who've ever seen a commercial lab testing concrete cylinders, they test them a little bit more rapidly than one every 3 days. Okay, so that's one of the reasons why the direct tensile test is not used for a lot of field applications. We will use a few surrogate tests. We'll talk a little bit about these. The flexural test and the splitting tensile strength test are two that we will use quite frequently. To go through very quickly, though, I want to talk a little bit about how concrete fails in tension. And while I'm doing this, I'm going to introduce another testing technique that you may want to be aware of. It's a technique called acoustic emission. The basic idea here is much like if I rip a piece of paper. If I rip this piece of paper, I'll do it really close to my microphone so everybody at home gets the same overall response. We have all heard that as I ripped this piece of paper, it made noise or released energy due to the creation of new surfaces. All right, so in this particular case, it was audible, so we could actually hear it, but many times it's in the subaudible region. But what is happening is you are creating a wave that starts propagating through the material. So that wave will either be audible or subaudible, so you've heard it here. It's basically the response of the material, energy is being released, so a wave starts propagating. Now what's going to happen is this wave is going to propagate to a series of different sensors. And if you can do two things. You can, one, listen for how many waves are created, and that will give you an idea of how many cracks are formed or how much energy has gone into damaging the material. The other thing that you can do is a technique called triangulation. Triangulation is used every single time the news reports tells us where the epicenter of an earthquake is. Right? Tells you that the earthquake happened at the 7-Eleven in the middle of the parking lot. Well, how did they determine that? They use triangulation. They have sensors set up. They figured out how long it took the wave to get to the different sensors, and then they back calculated. It's sort of like a high school, the high school math problem. You know, the train left going 20 miles an hour in this direction, 60 miles an hour in this direction. Where did it leave from if it got to Chicago at 3 o'clock and got to Memphis at 6 o'clock? Same type of problem here. Something happened. A crack was formed inside of the material. You know what time the wave was picked up at the different sensors. You can back calculate where it started at. What we want to do is I want to illustrate this to show this concept of localization a little bit more. And I'm going to show you a specimen that was yanked on in tension, or a tensile load was applied to fail this specimen. All right, the specimen is 5 inches wide, 125 for those of you who understand the metric system much better. It's a unit thickness. I believe it's about 2 inches thick, about 50 millimeters thick. And we are going to talk about a couple different types of deformation. We're going to talk about the load being applied in the tensile direction. So the entire thing is pulled under direct tension. There are going to be 4 displacement measures. We're going to be using LVDTs. They are going to be mounted on the surface of the specimen in 4 regions. We'll have LVDT 1 measuring this region, LVDT 2, LVDT 3, LVDT 4, and then I'll also be talking about the overall deformation of the sample. On the edges of the investigation area, there will be these different sensors that we're talking about to try to tell us where cracks are forming inside of the system. Now, one of the things that I'm going to mention here, I have drawn my own aggregates. All right, these are not necessarily where the aggregates occurred. I've drawn my own aggregates to try to show you what some of these different events may have corresponded to. Some of the different AE events are picked up inside of the sample. So here's a picture. The system is pulled on under tension. Each one of these little dots refers to a crack that's forming in the system. This is during the initial stage of loading, so what is likely happening is there is cracking that's occurring at the interface inside of the concrete. Now, a lot of people immediately say, aha, this is cracking at the interface. It must be because that is a weak region that we all know to be the interfacial transition zone. I would caution you to be a little bit careful on jumping to that conclusion. You have materials that have dissimilar elastic moduli. Right? Elastic moduluses, elastic modulum, whatever the correct plural is. All right? Stone and paste have different elastic response, which means that they are going to extend differently under the same load. So what's happening here is the paste is trying to extend. The aggregate under the exact same force is extending, but not the same amount, and you are going to expect to get cracking where materials are moving differentially. So even if the interfacial transition zone wasn't there, you would still get cracking at interfaces. Okay? So just because you see a crack doesn't mean that it's a weak region. It could mean that you have two dissimilar materials that are moving. Now, if we look at these LVDTs, and what I've done is instead of referring to them as LVDT 1, 2, 3, and 4, I've given them colors. So we've got the green, the black, the blue, and the red LVDT. If you look at these while the load is being applied, you can see that all of these displacements are relatively similar. The system is in the elastic region. You would expect to have the same amount of extension happening here as you have over here, as you have in the middle. So the entire material is deforming elastically. Everything is increasing with the application of the load, and you can see it starting to this upward trend that we see here. So instead of having load or something applied along this axis, I've just got time that the test was taking. Now, if you get into the second stage of loading, you're going to start to see clustering of acoustic events. This clustering of acoustic events is what we were just talking about before, where all of a sudden these interfacial transition zone events may start to now bridge the gaps inside of the paste, may start coalescing to get two cracks getting together and forming one crack in the overall system. Now you can see that you still have two different, the LVDTs are still all increasing, but they may be increasing at a slightly different rate. They may be increasing at the same rate, but they're all still increasing, so things still look fairly normal. They still look like what we would expect. Everything is still going into tension. I am now going to throw you for an entire loop. All right? Because what's going to happen in the third stage of loading is we are going to see a localized crack develop. That localized crack is going to start on one side of the sample typically and going to start to propagate across to the other side of the sample. A single crack in the overall system. And now when you look at the LVDT response, you are going to see that one of the LVDTs is still increasing. This one is still getting bigger. The other LVDTs, however, all start to get smaller. So this part of the concrete actually gets smaller. This part of the concrete gets smaller. This is exactly what we talked about earlier. This is unloading. So when this crack starts to localize, when the crack starts to propagate here, stress can't be transferred across that crack as much as it was before. So the stress here has to drop because this is in series with this part of the concrete. The stress here has to go down. The stress here has to go down. The stress here is decreasing because of the localized crack. The stress at the top is decreasing just because it's unloading. It's unloading. The LVDTs are tending to go back towards zero. Right? Just like we saw before. 1 second, Javier. In the pre-peak region, you have microcracking. You get up to the peak region, and all of a sudden, you've got the bulk material that's loading and unloading in an elastic fashion, and you've got a localized region where the crack is going to be growing, softening, and transmitting stress across that softened crack. Javier?
Is the displacement negative, really?
Isn't the displacement negative? Really?
Can you show the plot before? Two plot before, two slides before. One more. Other one. More. In the other direction. Sorry. That one. The black one looks like is negative displacement. Is that real?
Well, what's happening is, well, it all depends where you zero these. And typically when a lot of these tests are started, they're not started at an absolute zero. They're started with a little bit of force on the system, which is why they'll actually start to go back.
But theoretically, have to be
Theoretically, it would go back to zero and stop at zero. Okay.
So are you then saying that you could never get compression out of that portion of the testing material?
Well, this is a direct tension test. All right, and what happens is in this particular one, once this crack starts to form, you no longer have just pure uniaxial tension. You've got a crack forming on one side, and you're starting to bend the sample a little bit. So it's likely you could have a little bit of compression on the one face. But if you were just pulling it in tension, everything would stay in tension, but you'd still have unloading. Okay, I mean, I understand that we want to make sure that we understand what all the strains are doing, but the compression part, I think, is the minor part on all this. What we're really interested in is the fact that one portion of the specimen can behave entirely different than the other portion of the sample. This portion corresponds to the bulk, and this portion corresponds to the crack. Okay? Mike?
What is, I don't know if any tests have been done like this, but in your opinion, what does size effects do to this? Like, this is like a laboratory specimen that's this big, but say we did this to a gigantic column.
Right. Well, this is a huge issue because this is really, if you hear everyone in the industry talking about size effects, this is exactly what they're talking about. The real issue is that damage is localized to one region of the sample. So if this specimen were twice as big or 3 times as big, right? I make a bigger specimen over here. The localized region, the cracked region, stays exactly the same. The energy that's lost from this part of the sample is the same as the energy that's lost here.
I'm not talking about making it big just in one direction, but keeping...
I mean, we could scale it in different directions. All right? The big issue here is what happens is you get the rest of the specimen that's behaving elastically. And the reason that this becomes really brittle is what happens is the rest of the specimen is acting like a spring. All right? So this top part of the sample is essentially just acting like a spring. And now I say that, and a couple people are probably thinking, well, how does he think of that behaves like a spring? If I drew force and displacement over here, and I told you that the slope of this line was k, you would say, aha, it's the spring constant. All right? So what you have is you have a damageable material that's in between two springs. All right? In other words, you've got a damaged material in between two great big rubber bands that you are pulling apart. And you all know after playing with a rubber band, right, you pull that rubber band, you pull that rubber band, you pull that rubber band. When that rubber band snaps, it releases a certain amount of energy. Right? The energy that it's releasing is what's stored. Right? The energy is part of it's coming out of this crack, but there's an awful lot that's coming out of the unloading of that spring. So if that rubber band is getting bigger and bigger, there's more energy stored in that entire system that has to be unloaded. Okay, and that's where we really get into big issues. The other issue is as you get to bigger structures, this spark can be very, very small, so that the damage region can be really small, and it will look like a much more brittle material. Okay. All right, so we talked about Timoshenko. This is the basic idea of why we can't necessarily always assume that strain is a great descriptor of concrete, because the localized region where damage is occurring can dominate the entire behavior. Where the crack is occurring is incredibly important. All right? I understand that some of these concepts are not easy and some of these are going to take a little bit of thought. All right? But the idea is you can only use strain when the material is displacing uniformly. When you have preferential displacement in one region, and in this particular thing we're talking about displacement in the crack region of the concrete, all of a sudden the concept of strain becomes very, very muddy, because it says, how do you quantify that strain? What gauge length do you start using to describe it? And it makes the entire thing a little bit more complicated. Okay? Now, what a lot of people have tried to do is they've tried to break this up, and they've tried to use an approach called the cohesive law. So if you hear people talking about the cohesive law or the cohesive approach, what they're really doing is they're saying, we are now not going to use stress and strain to describe our material. We are going to use an elastic component, and we are going to assume that once the crack starts opening up, there is stress that can be transmitted across that crack. And regrettably, due to the time limit, you're going to have to ponder this and stay up late and worry about it over the entire spring break. But when you get back from the spring break, we will actually start to talk about models that enable us to do this, that break the material into the bulk region and the cracked region of our concrete. Okay, so everything through what I would say is probably the first half of this lecture is examinable on the first exam. Everything since we started to talk about localization, we will catch on the final. Have a good break.